discussion about Wi-Fi. So we were saying that the Ethernet's protocol of CSMA CD doesn't quite work in wireless situations, because when somebody is speaking, somebody is transmitting, they cannot hear anybody else. So it's hard to do collision detection because of that. Right? And also we saw situations where carrier sense may not work because you're just so far away from the other transmitter that you don't hear him. But at the same time, your potential receiver could be close enough to that other transmitter to face some sort of interference. Okay, so there are issues with carrier sense and there are also issues with collision detection. So the protocol which we came up with said that first of all you use acknowledgements, okay, because you can't do collision detection. You wait for an acknowledgement, and if the acknowledgement doesn't come back, then you assume that a collision occurred. Also we said that we can use something called request to transmit and clear, request to send and clear to send, RTS, CTS. So these are small frames which sort of reserve the channel. So RTS reserves the channel around the transmitter, and so let me just write that again here. So when A sends an RTS out, everybody who can hear him will remain silent for the period mentioned in the RTS, and when the receiver B sends out a CTS, just draw it this way. So this is the range of B, let's say. Okay, and this is the, let's say this is the range of A. And let's just say that B's range is something like this. So all others, let's say D over here and C over here, they are going to remain silent for the time mentioned in the RTS and CTS. Okay, so that way we took care of some of the issues that we had faced earlier, and we called this, the use of this, virtual carrier sensing. Virtual carrier sensing. So overall the protocol for Wi-Fi is called CSMA-CA, where CA stands for collision avoidance. So collision avoidance is a term used instead of collision detection. By using this RTS and CTS, we are trying to avoid a collision. Okay, so it's not collision detection when it happens, but you're sort of reserving the channel for some time with these frames, and so you're preventing collision. So it's called collision avoidance. So there are a few other things we need to discuss before we wrap up with Wi-Fi. So one of them is called the exposed terminal problem. So we talked about the hidden terminal problem yesterday in the previous class. So there we said that you have three hosts, right, and A and C are hidden from each other, they are too far away from each other. And this caused the hidden terminal problem where they couldn't carrier sense each other, and so a collision occurred at the receiver B. Right? Maybe both of them were trying to transmit to B, and so B could hear neither of them if they transmitted at the same time. So there's another problem. Of course, we handled this to some extent using RTS and CTS. So there is another problem which we are going to discuss today. So let's say that you have nodes like this A, B, C, and D. And let's say that each of them can hear the neighbors shown over here. So A can hear A and B and D, B can hear A and C, and so on. Okay. Now, in theory, what is possible is that A can transmit to D and B can transmit to C at the same time, and in theory data could be sent simultaneously this way, okay, because C and D are so far away from each other, okay, and in fact D is too far away from B for B's transmission to affect this particular transmission. Okay, so D can receive from A and C can receive from B simultaneously. And this is in theory, we are saying in theory, because B's signal does not reach D and A's signal does not reach C. I mean, this would be all less than noise, let's say, by the time it reaches C. So in theory, these two transmissions can occur simultaneously. However, because we are using carrier sense, this is not going to happen, because I mean we want to avoid this. So if we do carrier sense, suppose A is transmitting to D, B remains silent because it can carrier sense A. However, if A sends to D, then B remains silent. Due to carrier sense. Right, so this is called the exposed terminal problem. It wouldn't happen in an Ethernet bus, for example, because there the signal doesn't die out at all. So indeed, when A is transmitting, B better remain silent if all of them are connected by a wired bus. But here the signal of A decays, C cannot even hear A, and similarly D cannot hear B, so actually they could be transmitting at the same time. Okay, but because we are using carrier sense, the Wi-Fi protocol prevents this sort of a situation. Okay, so exposed terminal problem essentially says that because A and B are exposed to each other, they cannot transmit simultaneously. Okay. So this is a problem that the Wi-Fi protocol we discussed till now does not solve. Okay, so I mean, you can always think of some fancy solution which maybe will get it to work. Okay, but that may not be trivial to implement, and Wi-Fi in general doesn't allow two people who are within hearing range of each other to transmit simultaneously. So let's look a little bit more in detail about how exactly the frames are transmitted over the air. Okay. So every one of them will have something called a contention window, every particular terminal. I'm just going to call it CW. Okay. And what we are going to do, suppose we have several terminals, let's say A, B, E, C, D. Okay. So what did we do in Ethernet? So we said in Ethernet, if somebody has a frame to transmit, he could immediately send it out if the channel was free. Okay, so here we do things a little bit differently. So suppose there was a transmission going on. Okay, so suppose A to B's transmission was going on. Let's start with an ongoing transmission. So let's assume that the option of RTS CTS is there, RTS plus CTS plus data plus ACK. Okay, and like I mentioned earlier, RTS and CTS is an optional feature which usually is shut off. Okay, because it takes some amount of time to transmit this and it lowers the efficiency. Okay, but in principle you can have an RTS and CTS. Now what happens? So now let's say that A has more data to send, okay, to B, and here he has just sent one data frame, and so this is, let's say, C. So C is listening to the channel, so he does, he figures out that the channel is busy now, okay, because he can hear A. Let's say that everybody can hear everybody else. Okay, so what he's doing is he's doing carrier sense. Okay, so let's say that C has a frame to send. And so he is doing carrier sense, and he's keeping, he knows that somebody is transmitting, so he remains silent. Now he sees that the frame has ended. So what could in Ethernet, what would somebody have done? He would have just waited his appropriate 9.6 microseconds or whatever and transmitted. Here they don't do that. So both of them, let's say that A has a lot of data to send and C of course has got a frame to send. So what they are going to do is they are going to wait for a standard amount of time, which is called DIFS. Distributed interframe spacing. So you will see many terms like this with interframe spacing. Okay, we'll talk about SIFS in a moment. Okay, so there are these different time fixed, these are constant values. DIFS is a fixed amount of time, and both are going to wait for DIFS, and we'll see why a little bit later. But essentially this waiting time is going to give some particular host priority over others. So obviously if you wait for a shorter amount of time, you will be able to transmit earlier than the person who waits for a longer period of time. Okay? And in fact, if you look at this, so there is an RTS and there is a CTS, and there is let's say that there is a data and hack, right? So there is some space between these, and in fact the space between this is SIFS. It stands for short interframe spacing. So here you can see why this DIFS had better be longer than SIFS, because here you want this complete sequence of transmissions to complete one after the other. You don't want somebody else like C to transmit after the RTS is transmitted. Right? So C is listening, he's doing carrier sense. So he shouldn't see that the channel is free for a little bit of time and start transmitting. Then everything would go haywire. Since A has started transmitting to B, and even if the RTS CTS is not there, if somebody has transmitted data, you want the ACK to come immediately after that. You don't want somebody else to transmit in between, just because the channel is a little bit idle for a little bit of time. Okay, so a little bit of spacing is given between these frames corresponding to the SIFS, okay. And that is done so that is done for various reasons. So first of all, you want the other person to process the frame. Okay, so why do we need SIFS? So suppose A is transmitting to B. So B hears RTS, and what does he have to do? He sees that the RTS is for him. Okay, so here too we wait for SIFS. Once B has heard this particular time, this particular frame, he realizes it's for him. So he has to switch his circuit from receiver mode to transmit. I'm just going to say circuit shift, but basically what this means is, in his network interface card, he's got in the network, let's say this is the NIC, and this is going to the antenna. He's got one circuit to receive and another circuit to transmit, right, going to the same antenna. So he has to switch between these two. When he's receiving, this is sort of cut off from the antenna, and when he decides he has to transmit, he has to switch this on and connect here, right? So he has to do this connection quickly, right? So there is a circuit to enable that too, but it takes some amount of time to do this. Okay, and what about A? So A has sent the RTS. Okay, so A sent the RTS, and he goes transmit to receiver mode, and he starts listening. Okay, so this takes a little bit of time, and because of that you need a little bit of spacing, I mean, between both of these. So each of these particular parties, so B has to hear the RTS, it has to decode the RTS, realize that that RTS is meant for it, so there is some physical layer processing, some MAC layer processing. So let's just write that down. Okay, so people use the term MAC for DLL sometimes. Okay, they use it interchangeably. But in theory, the medium access is one part of the DL. Okay, but essentially, it corresponds to the DLL processing when they say MAC processing. Okay, so each of them has to take some action to go from, let's say, to go from transmit to receive and receive to transmit, and also B has to decode some particular frame that it has received. Okay, and similarly after CTS, A has to go switch from receive to transmit and then send out the data also. Okay. So a little bit of processing time is required, because of which you allow these frames to be apart by SIFS. Okay. So you don't want somebody like C who is not part of this particular transmission. He's neither the transmitter nor receiver. You don't want him to sort of suddenly start transmitting and interfere with this. So that is why C has to wait for at least DIFS time. The channel should be free for this much amount of time before he can even think of transmitting. Okay, so now, so let's say this transmission is finished, and DIFS is obviously going to be greater than SIFS. Because you want C to get less priority than A or B to transmit during this period of time. Right? But now that A has finished transmitting to B, B has finished sending back the acknowledgement, the channel is now free, and so every new person who has a frame to transmit will wait for this much amount of time. Okay. Now we do not want both of them to start transmitting. Okay, so in Ethernet it wasn't such a huge problem if two people start transmitting, because they immediately detect collision, stop, and then they back off and try to retransmit. Here that is a problem. If you let everybody start transmitting after this fixed amount of time, they will not know that a collision has occurred till, let's say, a long amount of time is over. Okay, because they detect collision by essentially not hearing the acknowledgement, right? So if you're sending an RTS, you know that the RTS has not got through only if the CTS doesn't come back. Okay, and RTS and CTS durations can be non-trivial amounts of time, because you're sending them at a lower modulation rate, as we said earlier. Right? And if you're not sending RTS, CTS, you send the data, I mean, it takes a long while for you to know that a collision has occurred. So we don't want them to start transmitting here. So right away we want them to wait for a random amount of time. Okay. So what we are going to do is, we are going to ask them to wait for random amount of time. And the question is, what should this random amount of time be? So first of all, what we are going to do is, we are going to divide time into slots. So let's say that this is a slot duration, and in Wi-Fi the slot is chosen to be around 9 microseconds. Okay, so it's very similar to the Ethernet time. Okay. So why 9 microseconds? Because if one person transmits in a particular slot, so suppose someone starts transmitting here, so someone starts transmitting, somebody else who's waiting for the next slot to begin to transmit should be able to successfully carrier sensed this particular signal. Okay, so let's say that A starts transmitting here, and let's say that D's wait time was 1x, one more slot than A. Okay, so D is going to wait normally up to this time, and if A had not started transmitting, he would start transmitting. Right? So we want D to be able to detect A's signal. He should be able to carrier sense A's signal. And we are assuming that they are within hearing range of each other. So this slot should allow D to hear A, okay, and not transmit. Okay, so this is a basic amount of time that we need. So why 9 microseconds? Well, first of all, you need to consider the propagation delay in the channel. So it takes some time, like we discussed in a previous class. So both of them, first of all, have started counting from a particular point in time, like we saw over here. Okay, let's say both of them are measuring time from some particular point. Let's say these particular points, but these two are not exactly the same, because maybe this frame took a little while to reach C. So maybe C has begun counting a little bit off from this, maybe a few nanoseconds or a few tens of nanoseconds off. Okay, so the slots first of all are not aligned. So this particular slot time might begin a little bit earlier, or depending on the situation, maybe a little bit earlier or a little bit later. Okay, so we have to take into account the time at which they start measuring to count their slots. Okay, so suppose this is let's say the 7th slot. They have started counting, like this is the DIFS. Okay, and since we were talking about C, let me say C's over here. Okay. So A started counting 7, 8, 9, and he's counted that after 9 slots I need to be able to I need to start transmitting. So he will start over here, okay, in this 9th slot. And let's say that this is what this is C's timeline, and let's say this is where A is counting, but let's say that C's particular slot, okay, might actually start a little bit later. Okay, so this may be his 8, this may be his 9, and so on, and this will be his 10. Okay, so in certain situations might be the opposite. Suppose this was C who was counting up to 9, and A, for example, was counting up to 10. Okay, so it might be a little bit different. This could be a little bit later or it could be a little bit earlier, depending on the scenario. Okay, so their slots are not aligned. So this signal will take some amount of time to reach the other nodes, plus the other node takes a little bit of time to do carrier sensing. Okay, so this should include the propagation delay, plus let's say possible offset. This is the starting time for counting for measuring slots. Plus the time to carry a sense. So the slot should allow enough of time for somebody who is supposed to transmit in the next slot to be able to detect that somebody else has started transmitting in the previous slot. Okay, so that much amount of basic time should be given in a particular slot. Okay, so also what else has to be done? So C must here A carrier sense it, that is in case A is transmitting. Okay, but suppose A was not transmitting. Okay, so if A was not transmitting, you never know, you still have to wait this much amount of time because C has to wait for some amount of time. Let's say that this is a propagation delay. This is the, let's say, the CS carrier sensing time. Okay, but what if A is not transmitting? Okay, it has to wait this much amount of time minimum. Okay, because you never know if somebody is transmitting or not until you wait for this much amount of time. And suppose A was not transmitting, then C has to go from receive to transmit mode. So you need to give enough of time for C to be able to do this too, and this is if let's say that nobody else was transmitting. Okay, so this will also take some amount of time. The let's say this, I'll just call it switch from Rx to Tx. So a slot time should be able to accommodate all of these, and the people who are designing the protocol realize that they would need up to 9 microseconds to do all of this. Okay, so that is the slot time. So what we are going to do is here is after the DIFS is over, we are going to wait for a certain random number of slot durations. Okay, so A is going to wait for a random number of slot durations, and C is going to wait for a random number of slot durations. So the question is, how much are they going to wait? Okay, so this is where the contention window comes in. Okay, and what we are going to do is we are going to initialize. Let me just say that what I am going to do is I am going to choose a waiting time. Let's say waiting, let me just call it the remaining waiting time. Let's just call that W. Okay. So this is initialized and we choose W from a uniform distribution 0 to CW max, okay, and this is multiplied by the slot time, which is 9 microseconds. Okay, so let's talk about this situation. So C has got a frame to transmit and A2 has a new frame to transmit, because the previous one was successfully transmitted. Okay, so this is a new frame. By new frame I mean he hasn't tried to transmit it earlier. So he's got a new frame and he initializes the wait time. Each of them initializes it according to this particular formula shown over. So you throw a random variable between 0 and CW max and multiply by the slot time. And for every idle slot, that you encounter, okay, we decrement W by 1. Okay, so let's okay, I think I need to write this a little bit, decrement it by, let's say, a slot. Probably the implementation would be this way. Let me write it this way, right? So the waiting time is actually going to be this much. So we decrement W by 1. Okay. Okay, fine. So let's, as an example, say that this is where that frame ended. RTS, CTS data plus acknowledgement from A, and both C and A have waited for 1 DIFS amount of time. And let's say that WA is equal to, let's say, 5. Depending on whatever these distributions are, let's say that C chose 3. So these are the slot durations. So this is where it's 3. Initially it is 3. And it becomes 2, and it becomes 1, and it becomes 0 over here. So now C can start transmitting. So if the RTS and CTS feature is switched off, C will immediately start sending with data. It would not send the RTS or expect CTS. So what happens here? So A has decremented his waiting time counter, and it is 2 over here. Okay. And so let's say that this transmission gets over. Sometime into the future. Now let's say that both of them still have data to send. Let's say C again has another frame to send, and A still has this other frame that he wanted to send. So this was, let's say, frame 1 of A, and this is frame, I'm talking about the data frame 1 of C. let's say was sent here, and A wants to send at this point in time the next frame, and C wants to send his second frame. Okay. So now both of them wait for DIFS. And again the countdown begins. So these are slots. So now let's say that now this is going to be reinitialized. Okay, so WC is initialized, let's say to 4. Okay, so this is the initialization. Now interestingly, Wi-Fi is not going to reinitialize WA here, because the intuition is that A has already waited. Suppose there are two people competing. You want A to get a better chance to transmit the next time, because he, poor chap, has waited and C has got a chance to transmit. So C is going to initialize his waiting time, but A keeps his waiting time frozen. So he starts from 2 again. So he starts from 2. So this was frozen and it becomes 210, and here of course this is 432. So A's timer has expired, so A can transmit now. So I'm just assuming it uses RTS CTS. This is a frame. The second frame of A is being transmitted. Okay, so this is how it works. Okay, normally, and of course C is going to freeze his counter here. Okay, so you decrement this counter only when you are in this phase. After your DIFS wait, only after that you start decrementing this. So for example, here there are some small gaps for SIFS between these frames. During those periods, WA is not decremented at all. Okay, so only after the DIFS phase, after A has waited for DIFS, only then he is allowed to start decrementing his counter, provided he does not carrier sense anybody during those particular slots. Okay. So this is how it works in general. So now, what about collision? Because it's possible that two people, even if within hearing range of each other, will have their counters expiring at the same time and they will transmit. Then there's going to be collision. And how do we detect collision? Well, you detect collision if you don't get an acknowledgement, or depending on that, right? Depending if you're using RTS and CTS, if you don't get a CTS, then you assume that there is a collision. Okay. So you sent RTS, but you did not get a CTS by the expected time, right? Or you sent data and you did not get back an acknowledgement. So it takes a little while, but you can detect that a collision has occurred. Now what do you do? So as we did in Ethernet, because there is collision, we sort of have to, in theory, wait for a longer period of time, because otherwise, we may again get a collision. So we want to be on the safe side. So what we are going to do is we are going to multiply CW max by 2. Okay. So this is in general what we are going to do. But at the same time, what we are going to do is CW max is maximum of CW max and some maximum allowed value, okay, depending on the particular protocol. Okay, and so what we are going to do is that we are going to multiply in general by 2, and but we are going to put a cap on it. We are not going to go beyond this maximum value. Okay, and then we are going to repeat the procedure again. Okay, and so we are going to carry a sense. If there is a collision, we are going to carry a sense. Okay, so I need to essentially during all this period, both are doing carrier sense. Okay, so F is sorry, A is going to carry a sense even here. So I should say this is A doing carrier sense, okay, for this entire duration of time. Okay, so here he is not counting down because the channel is busy, right? And he'll count down only after he waits this DIFS amount. So in case there is a collision, you're going to do the same thing. You're going to start carrier sensing, wait for a DIFS time when the channel is free, continuously free, and then you will start counting down. So to summarize, when we get a collision, what we are going to do is we'll repeat the original procedure. Okay, so what we are going to do is we are going to double CW max. Okay, and after this, what we are going to do is again we are going to choose the waiting time from a uniform random variable between 0 and CW max, okay, where the CW max has been updated according to this, right, according to these two rules. Okay, so you double it, but you don't go beyond the maximum allowed value. Okay, and essentially you wait for a DIFS free period, and then you decrement W every free slot. Okay, but if you find somebody else is transmitting, okay, if the channel gets busy, then what you're going to do is you're going to freeze your window, and then again you wait for a DIFS free period, and then again immediately after that you can start decrementing, right? And you transmit whenever W becomes 0. Okay, so this is the procedure we follow every time. Okay, so you always have to wait DIFS and immediately after that keep decrementing. If somebody starts transmitting, you freeze your waiting time, that particular variable. Okay, and then again you wait for DIFS, and then you can keep counting down after that. Okay, so this is how Wi-Fi's protocol works, and the protocol name is IEEE 802.11. Okay, so there are tons of different versions of this protocol. It started in the early 2000s. I believe B was the first one, but then you have G and N and so on, and AC. So pretty much every alphabet has been used. Okay, because they've developed Wi-Fi for different applications. But typically at home, nowadays if you were to buy a Wi-Fi access point, it would usually have at least N and maybe AC. Okay, and the latest standard is something called AX. So a little bit more about 802.11. This is what the frame looks like. So we have a preamble. So the preamble is going to contain some known signal which is going to help the receiver estimate what the channel is. Okay, and then after the preamble you have something called signal. And then essentially you have the MAC header. Which ends in the frame checksum, which is just a CRC. So this is 4 bytes. And inside this MAC header, or inside, I should say this is really the MAC part of the frame. So inside this you will have lots of fields, and it includes the MAC addresses of the sender and receiver. Okay, and besides that also you have the data and so on. Okay, so what does the signal contain? Well, essentially it's going to tell you a little bit about the modulation used over here. Okay, so I mean, we know that if the signal to noise ratio is good, then you want to use a higher modulation rate, but if it is not so good, then you would want to use a lower modulation rate. Okay, so it gives information about the modulation used and also something called the coding rate. So what is this coding rate? So typically what you do when you have a communication channel, you want to send across some information, and the channel may not be that great, so some bits over here when the information might get flipped, right? So what you do is that whatever data you have, first you code it, and that is what is put over here. So the coding essentially adds some redundancy in the data, and there are various codes for that. It's a very well developed field. So what is the rate? So suppose the rate is 3 by 4. What does this mean? So this means that suppose you send n bits, that means only 3 by 4 n, those n bits that you sent out only contain 3 by 4 n information bits. Okay, so you've added some redundancy, 1/4 of the bits you've added extra to whatever was there earlier. Okay, so again there are different ways of coding this. Like we've studied for CRC, of course it's a type of code, but there are various other coding schemes out there. Okay, and Wi-Fi typically would use something like 3 by 4 or 5 by 6. Okay, so this is what does 5 by 6 mean? That out of n bits, if you send n bits, out of those 5 by 6 n are information bits. Okay, so it's not that you just take the regular data bits and just add some bits to it like the CRC. I mean, you could send a completely different set of bits, but given the particular code word, you should be able to go back to the data. And as usual, we want to have the code words as far apart as possible, so that certain bit errors are not going to make you go from one code word to the one valid code word to the other valid code. Okay, so there are various 802.11 protocols, and let me tell you a little bit about some of the versions. So 802.11g uses 64 QAM with the rate 3 by 4, and this ends up giving us 54 Mbps as our data rate. Okay. Okay, so if you look at a particular frame, you look at this frame and you look at what is the speed at which you're sending data, that is going to be 54 Mbps. Okay, so this is not saying that if you actually run Wi-Fi, you have a mobile and you have an access point which is 802.11g, that you'll actually get a maximum rate of 54 Mbps. Okay, because these rates are excluding the waiting times in between frames and so on. So we said you have to have DIFS and then you wait a random time and so on, right? And that is going to reduce the overall throughput, right? Or the final data rate that you actually get at the application layer. So this is saying that during the frame, what is the rate at which you're sending data? And of course, there are different versions of 802.11, but you will see N typically on your router. So 802.11 is N is going to again use 64 QAM at rate 5 by 6. Okay, and let's see, 802.11 AC would use 256 QAM. And up to rate So this is the, you have you can choose rate 3 of 3 by 4, 8, 5 by 6 and so on. And 11AX, which is the standard that will probably be out soon, uses 1024 QAM. And rates, you can use various rates up to 5 by 6. So there's always some amount of coding that you do. Okay, and essentially the coding is going to help us do error correction. So it's not that we just want to detect if there is an error and get rid of the frame, because it's quite costly. We send a full frame after all. So what these codes help us do is that even if, let's say, one bit is in error, we will be able to find the nearest code word to that, whatever we receive, and we can do it really fast. Okay. So this is what we have, and besides that, what are the changes over here? Besides the modulation rate, you also have multiple antennas. So you have MIMO, which stands for multi-input, multi-output, multiple input, okay, I should say multiple. So what is this MIMO? It essentially says that your access point could have multiple antennas. So you actually see something like this on the market. You might see something like this, right, as your access point. So like 4 antennas, and your receiver too could have multiple antennas. You may not see it because it's let's say embedded inside your laptop screen or whatever like that. Okay. But you have multiple antennas, and that's going to make transmission much better. You can get much better performance. Okay. So because of this increased modulation rate and MIMO, you can get 150 Mbps here. And here you can get, let me see, up to, okay, so besides this is yet another thing beside MIMO. There is also the channel width. In megahertz. So 802.11g use 20 megahertz. Here we use a much, I beg your pardon, this is what I've written here for N. So for 802.11g it is 20 megahertz. For 802.11n it is 40 megahertz. Here you can use up to 160 megahertz, and here you can use up to again 160 megahertz. Okay, so you get gains due to various factors. One is you can use a higher modulation rate, okay, or a, let's say, a higher coding rate, and also you use more bandwidth. So what I mean by that is, suppose this is the 5 gigahertz range, and so one of these particular Wi-Fi transmissions can use a particular bandwidth. Okay, and so the width of this frequency band was originally only 20 megahertz for 802.11g, and it's gone up all the way to 160 megahertz. Okay, so effectively, if you keep everything else same, if you keep your modulation rate and the coding rate the same, and you use the same number of antennas and so on, your data rate at which you can transmit is proportional to the width. Okay, so if you use twice the width, you can get twice the rate. Okay, so here directly just going from 20 to 40 is going to double the rate, so we can get something like 108 just from that, right? And with a slightly better coding rate, we can get something like 150. Okay? But with the full power of MIMO and so on, you can even go much more than this. So you'll see advertised something like 600 Mbps, okay, for 2.11n. And that is in the case when you're using an access point and let's say your laptop or phone, which has a maximum number of antennas permitted by the particular standard. Okay, so in theory you can actually get even higher than this. Okay, and these are these rates that I have talked about. So this is 866 Mbps. And here I have in AX, it goes up to 1.2 Gbps. So these rates are only for single input, single output. So with just one antenna at both ends, you can get, in theory, these higher rates, because we're just using higher modulation, better coding rates and higher width of the channel, so we can push more and more information through. Okay, and you'd see advertised, of course, you'll see bigger numbers than these. You'll see 600 for 11n, and that is when you have the maximum number of antennas at the access point as well as in your mobile or laptop. Okay. So a little bit about DIFS and so on. I told you that DIFS is greater than CIFS, and that is because you want to give priority to somebody who's already transmitting to keep finishing the transmissions of RTS, CTS data and you don't want anybody else to interfere. So the way this is set is that DIFS is equal to SIFS plus 2 times the slot time. Okay, so you have to add at least one slot to give priority to somebody else, because a slot, we said, is required for somebody to figure out that somebody else is transmitting and not transmit, right? The person who's waiting DIFS, so this is SIFS. So let's say somebody is waiting for SIFS and then he starts transmitting. Okay, so let's say this is the data and this is the ACK. So this DIFS shouldn't be just epsilon slightly greater than SIFS, because then that person may not be able to detect this ACK. You need to actually sense the channel for some amount of time to figure out the other person is transmitting. So DIFS is chosen to be 2 slot times larger than SIFS. So somebody else is wanting to transmit, a data was sent and he's carrier sensing here. He senses nothing, but then he has to wait for this much time before he can transmit, and within at least 1 slot time he's going to figure out that somebody is transmitting. Okay. So we could have put just 1 slot time. So why is 2 put? Because there is something else called PIFS, which is SIFS plus 1 slot time. So this is like an intermediate priority uh, between SIFS and DIFS, and this P stands for point coordination function. So point coordination function we will not go into in this class, but essentially it's not a free for all system like we have here in the current Wi-Fi, where anybody can try to sense the channel and start transmitting. In point coordination function, there's more centralized control. So that option was given in the Wi-Fi standard, that if you want, let's say, the access point to control about who's going to transmit and so on with explicit messages, you could use point coordination. So that has intermediate priority. It definitely has more priority over somebody who's waiting for DIFS time. But this is rarely ever activated in your Wi-Fi routers and so on. Right? So what we use is the distributed coordination function. This is PCA. And why do we mean distributed? Well, because so one of the last things I wanted to talk about for 802.11 is quality of service. So think about it. Suppose you're using Wi-Fi and you're actually having a conversation with somebody. It may be, let's say, a Meet call or whatever, right? MS Teams call, and you're doing it over Wi-Fi. And somewhere you have here, let's say this is your access point. So what is happening at the MAC layer? So you're not immediately sending out your packets. You have to wait. You have to do carrier sense, wait for the channel to be free, then wait for some more time. If there is a collision, then yet again you have to sort of choose your random variable, random waiting time from a larger distribution and so on. So there are no guarantees for packets to get through. And that could be a big problem, because if your packets are delayed by a few 100 milliseconds, your voice packets, then the quality of the voice conversation is going to go down, and even the quality of the video. Okay, so you want the latency of packets to go from here to here to be quite small as possible. So what if there are, let's say, multiple people competing? Suppose somebody else is using the same access point. Is there a way to give higher priority to somebody, let's say somebody who's doing a voice call, over somebody who's, just say, transmitting a file? So is a higher priority possible in order to give the appropriate quality of service to an application? So how would you do it? So I think I've given out enough secrets, in fact, to say how it might be done. So we said that over here, when we were talking about DIFS and SIFS, somebody waiting for only SIFS has a clear priority over somebody who's waiting for DIFS amount of time. Okay? And that is because the other person is waiting for a longer duration. So definitely this person will start transmitting earlier. So there was a protocol called 802.11e, which was created for this purpose, and it doesn't give a hard guarantee to some applications over the other, but what is suggested is that your CW max value should be like this. It should have an initial value and there's a max value. So what it says is that if you have a voice application, that you should have initial value as 3. Okay, you set CW max equal to 3 while choosing your waiting time, and the maximum is 7. Okay, so you're never waiting for a very large amount of time. And if you have video, you would have to, you could choose from this. So this is clearly giving at least in a probabilistic sense, it's giving a higher priority to voice over video, because the voice packets can get through quicker, because the random wait size, remember, is chosen from 0 to the CW max value, right? So we said W is chosen from uniform 0 and CW max. Okay. So this is 15. And other applications, you give them even lower priority, 15 and 1023. Okay, so this way, on average at least, you would expect a voice packet to get higher priority over a video, which will get a higher priority over any other application. Okay. So this is, of course, it's again not giving any guarantee that your voice packet will get through, let's say, in 50 milliseconds or 100 milliseconds, but it still gives it a higher priority over other competing packets. Okay, and the question is how does the MAC layer know about this? So this, I mean, you rarely find this implemented, but how does the MAC protocol, I mean the data link layer, know whether it's a voice packet or the video or something like that, right? Where is that information coming? And so this would need some sort of a cross layer interaction, which we were trying to avoid as much as possible in the internet designs, but we need some cross layer interaction. So the application layer would somehow have to tell the Wi-Fi layer that this particular packet is a voice packet, and so, right? So it turns out that the application layer can access the IP packet fields, certain fields. Okay, you can do that, and the application would have to give that information in the certain field in the IP header, which this DLL layer will actually have to read. Okay, so it's quite a cumbersome thing, because DLL is the opposite end of the stack. Application is right at the top, and application would have to communicate with the data link layer in some way. Right, so this, in theory, this protocol is out there, but it's rarely ever used. If you are doing a voice call and somebody else is transmitting a huge file on Wi-Fi, the chances are that your voice call might actually end up being pretty bad. Okay, so if you want good quality of service, then Wi-Fi is not something you should opt for. Okay, you might there may be some other protocol which you can use at the MAC layer, which will give you better quality of service. Okay, so what I haven't mentioned, a couple of miscellaneous things, that SIFS value is 10 microseconds for 11G and 11N, and for the latest protocols it's a little bit higher, for I think it's 16 microseconds for 11AC and so on, right? But anyways, this is one miscellaneous point. And another thing which I haven't mentioned is that just like in Ethernet, here too you have a maximum number of attempts to transmit a frame, and if you have more than that many number of collisions, you will actually stop transmitting it. Okay, so there is a maximum retries. Okay, if there are collisions, and then you give up transmitting a particular frame. Okay, so this is all that I wanted to talk about Wi-Fi, and every Wi-Fi protocol tries to be as backward compatible as previous Wi-Fi protocols, right? And so the frames that you see today will look similar to the old frames, but they may have certain fields added and so on. Okay, and Wi-Fi has become very, very popular, of course, just because it's fairly easy to set up and it doesn't require much coordination to get working, especially if you're using the distributed coordination function. You can just get set up an access point. Maybe you have to do a little bit of configuration, but then you're good to go. Okay, so in the next class we'll talk about some other wireless medium access control protocols, for example those that are used in 4G and so on.